So, welcome everyone to our second part of the last day of the OSDC. I hope you're all well fed and ready for Sebastian Saemann's talk about his experiences when developing a SaaS platform using open source tools.
Thank you. Can you hear me all right? Okay. So, welcome everybody to this talk. I hope you're doing good and you enjoyed your lunch. I'm pretty excited to be here. And so thank you for joining my talk. So before I want to start, I want to do a quick poll with you. Who had a good time last night at the OSDC evening event? So please raise your hands and keep your hands raised, because there are following questions. So, okay, so almost everybody. And who enjoyed at least one alcoholic beverage last night? At least one. Okay, more than one. Okay, more than two? And who is running containers in production? Okay, so perhaps we have a connection between drinking and running containers in production. But anyway, this talk is about how we are running containers in production. I want to show you some components and technologies we are using, and share with you some experiences we made while we were developing a software as a service platform based on open source technologies. This talk is split into 3 pieces, so I just start with a quick recap, so clarifying what software as a service means, and show you the architecture we are using and how we developed the platform itself. But first up, who am I? My name is Sebastian Saemann. I'm working as head of managed services for NETWAYS. So I'm leading a department of 4 teams. But basically, I'm a systems engineer, so I'm an operations guy. And yeah, so you can also find me on Twitter as well. I think almost everybody knows NETWAYS because of this conference. But in a nutshell, we're just awesome. And yeah, we have an events team, which is hosting such beautiful events like this. We have a consultancy team. We have a dev team, development team, which is contributing a lot to the open source monitoring project iSinger. And we have a managed hosting team. This is the team that I'm leading. And this is mostly what I'm talking about. So like I said, nowadays, everything is a service. And I want to clarify where the differences are between the most popular ones. So the most popular ones are infrastructure as a service, platform as a service, and software as a service. And of course, you can run your application or your tool stack on premises. So as you can see on the slide, there are different responsibilities who needs to take care about which layer. So if you're running your application on premise, you have the full responsibility from networking up to storage, up to the servers, virtualization, operating system, and so on and so on. And if you don't want to do that, you can rely on popular cloud service provider, public cloud service provider like Azure, Microsoft Azure, AWS, Google Cloud, and so on. They will then take care with their engineering team up to the virtualization layer. And yeah, if you want to use a platform, so for running your PHP application or your Ruby on Rails application on top of a environment, you can use some platform as a service provider like Heroku, for instance. And last but not least, we have the service, software as a service part, and there the provider takes care about the complete stack. So even your data and your application is in the responsibility of the service provider. That means it has to back up your data, it has to upgrade your stack, your application, your runtime, the operating system, so the complete stack, and you are just using and consuming the software. So what's the motivation for us to build a software as a service platform? Nowadays, IT is using more and more cloud, of course, but what you can see is that IT companies do have less fear and are more interested in running public cloud services because of potential money savings, of course. It's easy to use and a lot of other things. But when you look at the European market, or especially the German market, we are always afraid of running something in the public cloud on US companies and stuff like that. But this is shifting. I think it's shifting because banks and insurance companies and other companies like this are running applications in public cloud in public clouds. And besides that, we had a lot of customers that were asking for hosted apps, and that's why we built a software as a service platform. Oh, sorry, skip this. So what is NWS? So NWS is the NETWAYS Web Services. This is a platform where we are hosting your favorite open source application. It's pretty new. We just launched it in March this year. And how it looks and how it feels and what it has to offer, I want to show you in a quick demo. Okay, so this is the landing page. You can reach us on nws.netways.de. And if you scroll down a little bit, you can find our apps that we are providing right now. So there are more coming soon, but for now we have 6. There is, for instance, a GitLab instance you can run on our system. And this GitLab instance comes, for example, with a GitLab runner where you can run your builds on top of it. It's already pre-configured. And we have a Docker integration where you can use the Docker registry, and this Docker registry is backed up on our S3 or Swift storage. So I think my sound is working. Sorry for that. Okay. Okay. This is GitLab. And there are other tools like iSinger2 Satellite. If you're having already, or who knows iSinger2? Who runs iSinger2? Okay, for those, the iSinger2 Satellite can be a good extension because you run or you can monitor your services from a different perspective. That means you can extend your existing monitoring system by running a satellite in a specific location. So we are now offering North California, Japan, and our location in Nuremberg. And yeah, it can be handy to check from a different perspective how your website is running from there, for instance. Okay, so, and if you want to try it out, you have, of course, to log in. And this is the backend. So this is just a demo card, so don't. And we have a Rocket Chat instance. So Rocket Chat is a chat. And you can see your running apps listed here. So you can add more if you want to. And your Rocket Chat or all the other applications would look and feel like this. So you have your own instance. You can do whatever you want with it and just use it. So this is what we have to offer. And what we are doing with this Rocket Chat installation within our platform is that we have a little, here it is, live help desk chat. So to provide our customers, and this is running within our own, or this is our own product, which is backing up this live chat here. Okay, so when we started developing this platform, we started completely from scratch. And starting from scratch always means a lot of fun, most of the time at least. And because you don't have dependencies, so you don't have to move or migrate customers or data or something like that. And you have the feeling you're building something big, so you don't have to look for, or you should not have to look for copy and paste how-tos on Stack Overflow or something. So you just decide which tool is the best for the job. And you think about it, you discuss about it, and in the end, you will have a blueprint. And within this blueprint, we had some specifications. So our platform, everything needs to be in version control. So in Git or SVN, in our case, of course, Git. And it should be redeployable. We wanted to have a test-driven approach, so test-driven development. We think it makes you confident in changes. And it's a good approach, of course. And to be honest with you, I'm no professional software developer, and neither my teammates are, because we are from the operations background. But in time of DevOps, I'm already confused. So Next is agile. We wanted to do everything very agile. That means we have weekly sprints. We are defining within the sprint a user story. For instance, I don't know, a customer should be able to log in, and then we are realizing this feature from milestone to milestone. The reason for that is it's not super hipster, it's just because we had no clue how the whole thing would look like, and that's why we moved from step to step and decided from week to week how to go next. So it worked out quite well. And last but not least, the microservices. We just wanted to fully benefit of the advantages of the microservice approach. Okay, let's talk about infrastructure as code first. We have two worlds. On the left side, what you can see here is we have a private cloud based on OpenNebula. It's supported by Foreman, so Foreman is managing the life cycle of a virtual machine and is declaring some roles. So you are a executor or you're a hypervisor, whatever. And this role is then configured by Puppet. So this is the stack what we already had. And on the other side, we have the locations what I was showing you in Japan and in North California. We have, of course, no data center there. That's why we are using or make use of the public cloud of Amazon. And because we don't want to reinvent the wheel, and we have a lot of Puppet modules, that's why we gave Packer and Terraform a try. I think almost everybody was in the talk of SaaS yesterday, I guess. So with Packer, it's a pretty cool tool to build Amazon AMI, so golden images, and we can reuse our Puppet modules there. So with Packer, you're launching an EC2 instance, and then it gets it pulls the Puppet modules or pushes the Puppet modules, and it applies all the Puppet modules within this virtual machine, and then saves this state back to the new AMI that is, or to the golden images that we can use then. And Terraform is a tool for configuring and defining your virtual infrastructure within AWS or Google Cloud or other providers. So, and how Terraform is working for us, I want to show you in a quick demo. Okay, so like I said, everything has to be in version control. This is a Git repository, and within this Git repository, there are my Terraform files. So, just a second, I have to switch my, okay. So there is a Terraform configuration file, and within this Terraform configuration file, you can see some variables. And you can see something like this. So this is the resource which is configured or is going to be configured within AWS. So a launch configuration, what is launched there. We have autoscaling groups. Those autoscaling groups have a size of, please don't use more than 10 virtual machines, but at the minimum 1, and so on. So next would be the VPC, so the virtual private data center. I don't know how they say it. So it's your private data center, and there are of course some gateways, some routing tables, some subnets, all the stuff. So a VPN connection to our location in Nuremberg. So you can all the things can be defined within this configuration. And as you have seen, there are some variables inside there. And those variables come from a variable file. And within this variable file, we have locations. So we have a key. It's US West 1 or Asia Pacific Northeast 1. This is the location of Amazon. And we have as a value different AMIs, for instance. We have different availability zones as a variable. And we have different subnets and stuff. So if you have a look at the diff or at a Git diff, what I was preparing you for the demo, we are now launching a VPC in Frankfurt, And all I have to do with Terraform is just to add some new variables in my variable file. So it's not really more than that. So that's it. Okay. And if I'm running this command right now, so I'm using the Terraform binary, I'm using the command plan. This is more or less like a dry run, which is showing me what it would do on Amazon side. And I have a variable file where my Amazon key is stored, so my secret, and a state file. So this state file is going to be used for every location so that Terraform knows what should be configured or what is configured. And usually, it should show up within a couple of seconds. There we go. And what you can see here is basically the things what Terraform would do with Amazon. And it would create a VPN gateway. It would create some routes. The main VPC, of course, the subnets, security group, so all the stuff what I was declaring within the Terraform configuration file. So that's pretty cool. And if I want to do so, I would just hit the apply. This apply would take about 5 to 10 minutes, and then my location is ready to go. I don't show this in the demo, but you can imagine what will happen. And if you want to get rid of it, you have the destroy command, and Amazon won't charge you anymore for the used resources, so it's pretty cool. And what comes also very handy is that you can use the plan or the apply command if you're changing your infrastructure later on. So you're just changing the Terraform configuration, and then you can do a dry run, and you can see what will happen on your infrastructure, and it will get configured. So it's a good tool. It's a perfect match for AWS, in my opinion. This was the demo. Okay, so now we have the virtual infrastructure. So we have the private cloud based on OpenNebula with Foreman and stuff, and we have the AWS side. And on top of this, on top of the cloud, there are running virtual machines, and our stack looks like that. We are using Ubuntu as an operating system. We wanted to use CoreOS first because we are just running containers in the end. But Ubuntu just fits our needs better because we have, like I said, a lot of Puppet modules, and they take care about monitoring, backing up, and stuff like that. And we would have to reinvent the wheel for CoreOS in this case for us. And the team know-how is just better with Ubuntu than with CoreOS, and that's why it was an easy decision. On top of Ubuntu, we have MESOS installed. I come to this just in a second. And on top of MESOS, there is Kronos and Marathon. So those are frameworks on top of MESOS. Just a quick question, who of you know MESOS? Okay, cool. So this is a typical architecture of MESOS. So MESOS consists of master daemons, usually at least 3 over there, and you have slaves. So that's over here. And you need a zookeeper for quorum and for leader election, and to prevent you from split brain. Also 3 at least. Then you have a framework on top. So in this case, it's Marathon. You can use Kronos, you can use Elastic, Jenkins. There are plenty of frameworks what can use the MESOS resources. And usually a framework comes with a executor on the slave. So in our case, this is the Docker executor. And if you want to start a task, so a container in our case, the communication is like that. The MESOS slave will report its resources and back to the MESOS master, and the MESOS master then will offer those resources to Marathon. So for instance, I have 4 GB RAM and 4 CPUs free on my slave, and those resources are going to be offered to Marathon. Marathon then, so the scheduler or every other framework there would then decide if those resources are good enough. So you can use location constraints or something like that. And if they fit, it will tell MESOS, and MESOS will then start the container on a slave. Yeah, and like I said, Marathon and MESOS have to communicate with Zookeeper because of split brain, leader election, and stuff. Okay, so with Marathon, so with the framework, Marathon is the framework which keeps your tasks running, as the name would suggest. You can create Docker containers, and it's pretty easy because you have a JSON hash and a good REST API. And this JSON hash over there just says, please create an app called production/nws netways.de and some more parameters, so some cgroup limitations for memory and CPU. And it will tell, use the Docker executor, so on the slave. And then there are some Docker parameters. And if you, I think you know all Docker and the CLI, it should look like familiar to you. Okay, and if you do this multiple times, or you're posting and posting and posting some JSON hashes with, of course, different names to it, you will end up like this. So you have a lot of containers, Docker, 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 and those bunch of containers are across multiple different nodes running on random ports. So it's a totally mess if you don't have a clue and a mechanism who takes care about this. And in the end, you will end up with some questions. And those questions can be how to deal with container interconnection, how to deal with data persistency, and how should I deal with service discovery. I start with interconnection first. So container interconnection means one container should be able to talk to another one on a different host. So it should address the container by its assigned IP or its DNS name. But some of the containers should not be able to speak to other isolated groups. So this is the what we want to realize. And for this, we are using Docker Overlay Network. The Docker Overlay Network feature was announced and released, I think, in Docker 1.9, 1.10. And yeah, it just comes with Docker. And it's really easy to run such complex network with virtual extensible LAN. So the VXLAN is an industry standard. It's basically like a ordinary VLAN, but it's across broadcast domains. You could say it's a VLAN on steroids, or in other words, it's a layer 2 on top of layer 3. So it works like this. You have those two containers, container A and container B. They are running their own IP address range, and they want to communicate with each other. And they are running, of course, on two different nodes. And those nodes act as a VXLAN endpoint. So the VTEP is the VXLAN endpoint, and they will communicate through their IP addresses. So the original layer 2 frame of the containers will be tagged with a VXLAN tag or with a VXLAN ID, and then it is encapsulated in a UDP fragment, and this UDP fragment is then, again, encapsulated in IP. And this IP, you can route it elsewhere. And so you have a VXLAN or a virtual LAN on top of layer 3. So it's pretty cool. Data persistency, sorry. We want to keep data or important data in case of a node failure. So your container is running usually on the local disks, and if this node is failing, you can start the container elsewhere, but the data would be missing. And for this, we are lucky enough to have a Ceph storage. Who runs or knows Ceph? Who knows Ceph first, perhaps, and then who runs Ceph? Okay, cool. Ceph is basically a distributed storage cluster, so it's software. And with that, we can make use of Ceph RBDs. We are using also a Docker feature. It's a Docker volume driver plugin, and we are using from this handy guy. He's called Porcupine, and this is basically a fork of the Yellow Pages engineering team where this project was originated. But the GitHub project seems more active and more maintained on the Porcupine stuff. So if you're interested, go for that. Okay, and how do we use it? We just extend the JSON hash. So the JSON hash at the beginning, we just add some more Docker parameters to it, and we say, please use the parameter Docker volume driver, RBD, it's then called RBD, and mount this RBD onto the container mount point. A RBD is basically a like a iSCSI block device, and you can, it works like a block device. Okay, next thing is service discovery. Service discovery means how to route or forward traffic to containers, because containers are spawned on random ports, on random nodes, and that can be tricky. And for that, we are using HA proxy in combination with Marathon LB. Marathon LB is basically a Python app that is managing your configuration of HA proxy, and it consumes the app state of Marathon itself. So it connects either with polling or with a subscription to the event bus of Marathon, and then knows what apps are running and is configuring HA proxy accordingly. So you can run it with that, or you can use some other tools like GoGetter or vulkand or whatever load balancer you want to. But those almost have a direct dependency to your key value store, like etcd or zookeeper. And if your etcd and zookeeper is crashing, your load balancer would also. So in this case, we have the configuration already. Yeah, it would be also a mess, but what's running there, and it would keep up running. And another good thing is by using HA proxy, it can forward all kind of traffics. So it's not restricted to HTTP like most of the others. So it's cool for us. And in the end, you have a complete setup. You have container interconnection based on Docker overlay network. We have the persistent storage with the RBD stuff, and we have a service discovery. And the cool thing is we can scale this horizontally. So that means if we need more computing power, we just add more slaves or more virtual machines in our case to the MESOS slaves. And if we need more I/O power or more volume inside of the Ceph storage, we are adding more Ceph nodes to it. So yeah, it's cool. It's pretty complex, I would say so. There are a lot of interactions going on within this setup, but it's very easy to use. So if you're developing with this construct, it's pretty easy because it has good APIs. And how those APIs are working, I want to also show you. Yeah. Okay, so this little tool is called Postman. Okay, it's too small, isn't it? I can't really make it bigger. I just read it what stands there. So it's a JSON hash, and there are some informations inside of it, and we have some informations like the app name. So there is OSDC my app. We have the C group limits. It's basically like that what I was showing you in the slides, but it's more comprehensive. We have some location constraints. So this container or this application we want to run is just run in our data center in Nuremberg. And then we have some Docker parameters, so Docker executor stuff. We want, or in this demo, I'm running a nginx container, so it's nothing really fancy. But I'm loopback mounting the etc host name of the MESOS slave inside of the container so that we can see if we are visiting the container's web page where we have landed. Then we have port 80, which should be exposed, and it should not be privileged, of course. And we have a parameter. This is very interesting because this is the network stuff. So we just say, please use the network OSDC my app. And this is a Docker overlay network which I have created already. please use force pull image. That means if you're restarting the app, it always tries to pull the image of the Docker registry. So if you're having a newer version, it would use it. Okay, what else? We have some health checks. And what's also important are the labels. So there, it's very blurry. It is myapp.nws.netways.de. This is the HTTP address where I want to reach this container. Yes, it's basically a HTTP post to this endpoint, and if I'm going to send this, I have to be quick. Okay, I was quick enough, I guess. So there we have a new deployment popping up here. This is the Marathon web interface. And it is starting, so it already started the container, and now it runs for the health check. So it checks if this container is healthy. And as you can see, this container was started on MESOS slave 11, in this case, on a random port on, I don't know, 32848. And if we are visiting the website, we have the etc hostname, what I was remounting. Okay, and if we have a closer look, we can see the container running on top of NetMesos slave 11. And yeah, this random port, which is exposed to or is forwarded with destination NAT to the container port 80. It is using the nginx stable Alpine Linux image, what I have defined, and so on. And if we have a closer look to this particular container with Docker inspect, we can see also that it's running within my container network OSDC-myapp. Of course, I can grab some information out of it, so I just send a GET request to the endpoint, and then I get this JSON. So it looks pretty much the same what I was posting to Marathon API, but it has some more information, like it's very blurry, sorry for that, when it was started and stuff like that, so it's good for developing. And if you want to scale it, so if you have load on this nginx container, you can scale it very easy. So you just have to send a HTTP put request. So you're changing the original JSON hash. And in this case, I'm adding this value. So it's key instances, and I want to have 6. And if I'm sending that, there should be a new deployment going on there. So all those containers are staged right now. Some of them are healthy already. And here we go. So what you can see here now is it's MESOS slave 6 involved, it's 8, 7, 10, so it's just random nodes on random ports, like I said. And if we go back to the web page and we are reloading, it is just load balance. So the HA proxy stuff with Marathon LB is just working like it should. And if we go back and we have a closer look inside of the Docker network, OSDC myapp, we can see, so this is a container name with this IP address, and this is the next one, and this is the IP namespace, and this is the container interconnection. So every container can connect to the other one through Docker overlay network with VXLAN. So it's pretty cool. Okay, and of course, if I want to get rid of it, I just send a HTTP delete request to the endpoint. Here. And it should be gone. Yeah, now it's gone, so no applications are created. Okay, so this was the architecture part. I'm going on now with, so this should look like blurry, so this is just an effect. So we started with developing, and our first steps in development, or our first step was to declare a programming language, a primary programming language. we have chosen Ruby for our stack because, like I said, we are now professional software developers, and it's our most well-known language. We can do so, and it's pretty mature. And with Ruby on Rails and Sinatra, you have good frameworks to build APIs and to build all those REST stuff. In the beginning, we had to deal a lot with database models and relationships, the active record stuff, and how to handle cachings and sessions. So all those stuff was defined. And because we wanted to have a test-driven development, we just built the test pipeline first before we started developing. So this was pretty cool because with every Git commit, the pipeline was triggered in the background, and you're getting confident, even more confident from commit to commit. And the best is you don't have to fiddle around and deploy something manually. Usually you have, you're committing and pushing to Git, and then you go to Marathon and you're doing something like, I don't know, restart, Docker, blah, and yeah, it's pretty cool. And this helped us a lot, especially in the beginning. So when we were changing the database model a lot and we were refactoring, all those test-driven approach helped because it just says here is something broken there and so on. So it was quite cool. Within this pipeline, we have 3 environments. Nothing really fancy. We have a local development, so you can run the complete environment on your local laptop. You can either run Docker containers, or you can run your applications natively, so your Rails or Sinatra stack or whatever. I prefer that, to be honest. And you can run, we have some vagrant boxes that can be provisioned with the production Puppet modules. And then you go and have a MESOS cluster on your laptop within VirtualBox. It's pretty cool. And in testing, we have a database which is seeded from scratch on every deploy. So we have some test data within. And yeah, it just increases the confidence. And to push in production, still manually, we have all prepared, but it's a click in the web interface of Jenkins. We don't trust us, we don't trust the tests, and yeah, we want to have the control over this not to push something bad into production. The pipeline looks like this. So the Jenkins pipeline, it's also nothing special, I would say. But we have this pipeline for every environment. So if you're running in development environment or in testing and in production, every time or your source code goes to this pipeline. So every change in the Rails application or in Sinatra containers are triggering unit tests. So those are triggered by Git, and Jenkins are running or is running those unit tests. And then a Git Docker image is built from that. So we have Docker files, and the native Rails app will be wrapped in a Docker container. And this Docker container is then going to be pushed to the Docker registry, and from that it's going to be deployed also with Jenkins to the specific MESOS environment. And within this environment, there are running more and more tests, so end-to-end tests and integration tests and stuff to check for stability. Okay, and like I said, we wanted to make use of microservices. You have a lot of pros and cons of microservices. Some negative aspects are it's more complicated. You have some, if it's important for you, you have network latency, of course, and you have a lot of overhead in the code. If you're just building a small microservice, you have a lot of code which is dealing with the API, and it's more complicated in debugging, from my point of view. And for debugging, we have a lot of logging, and we try to log everything, every event out of our Ruby code to Elasticsearch to know what's happening within the containers. Because if you don't know the complete stack and all the microservices, it's sometimes very hard to get an idea which microservice just failed right now. And that's why it's pretty important to log all those events. On the other side, it's easy and fast to develop. That means you can focus on one thing. So you're doing is you're creating an API for something, and you're just doing this something. So it's pretty fast forward. And the microservice architecture allows us to switch the programming language. That means if we, as non-professional developer, think writing something in Go or in Python would be better because there is a better framework or better libraries, we can use just Python or Go for that. Okay. So those are our microservices. Every microservice has a defined interface, so it's a REST API in the end. This REST API is secured by SSL client certificates to make sure no one can talk, of course, to our API. And it's exchangeable. We had some issues by providing the payment stuff, so we started with PayPal, and it all worked great in the sandbox. But then when we wanted to go live, PayPal said, it's not working in Europe for you, sorry. Yeah, it was a mess, and I was really angry. But technically, we just had to exchange this payment or this PayPal microservice with a new one, with the new payment service provider. And we don't have to refactor the app because there was something special to PayPal or something. So if we want to integrate more payment service provider, we can also use more microservices, so it's pretty cool. So it's exchangeable, and like you have seen in the demo, it's scalable. If we have some issues while generating PDFs, for instance, for the billing process or something like that, we can just spin up more PDF microservices, and the load balancer will spread the API calls to multiple instances. So what's next? We are planning to build, of course, more apps, even more sophisticated ones. Let's see what we don't know yet. If you have a good idea, just talk to me, perhaps. We want to provide some infrastructure as a service stuff within the platform because the platform is very flexible, and we have already code which is managing our infrastructure as service part of OpenEbula and stuff, and we can just reuse it. And we want, of course, gather more experience, so our customer needs and stuff. And with that, we want to add features to the products, extend the products, and add features to the platform. A little bit early. That's pretty much it. So if you have questions, feel free to ask them now. And try our products if you want to. We have a booth already over there. I think you have seen it. And thank you for listening.
So thank you very much, Sebastian. Also, when you're over there ordering your 20 single satellite AWS instances, you can also take the chance to join the raffle of Thomas Krenn. It's the last chance before the winner will be selected. So, any questions? I think you were the first one.
So you mentioned you're using Ceph for persistent storage. Yep. I expect you do that in AWS as well?
I didn't mention that. In AWS, we are just launching stateless apps for now, so we don't use any persistent storage layer there. So in AWS, you would use the, elastic block device of AWS. It would act like Ceph RBDs.
And so you're using your local in-house Ceph cluster for those stuff? Okay.
Yeah.
Thanks.
Thanks for your talk. I've actually have 3 questions. So, why did you decide to use MESOS instead of, for example, like Kubernetes?
Okay. Okay. Let's start with the first one. It's a good question. You have Kubernetes, you have Docker Swarm and MESOS right now, so it's like a orchestration war, or container orchestration war. When we have evaluated MESOS, it was just with the Marathon API. It was just very. It's not stable because it doesn't feel like stable, but it's very flexible, and we don't have the use of running pods. So you can run pods as well there, but you need to have a complicated network with Kubernetes, and that's why we go with MESOS. And of course, you can reuse MESOS resources with different frameworks. So we had a project where we wanted to scale out our Jenkins, and Jenkins then can talk to MESOS and get more resources and spinning up more Jenkins workers there, or Jenkins slaves, I don't know how they name it. And yeah, it's more flexible, in my opinion, but I guess it's just tomato. Yeah.
So the second question, what are you using for log management for your MESOS installation? Like, do you collect them somewhere centrally, or what's your
it's Elasticsearch, so it's Logstash and Elasticsearch.
And last one, so you have your own services, like to manage your infrastructure, and then you also have the client apps, right? Like the Rocket Chat or GitLab,
right.
And they both run on the same MESOS cluster?
They run on, right now they're running on the same MESOS cluster. We want to isolate, or we are isolating them with IP table rules, with namespacing, with Docker user namespaces and stuff. And yeah, you could run virtual machines for that. For the GitLab runner, we are running virtual machines because within this GitLab runner, you're executing code of the customer, and that's very dangerous. And yeah.
Okay, thank you.
You're welcome.
All right, any more questions? No, it doesn't look like that. So I'll see you in the next talk.
Thank you.